Good morning, everyone.
Good morning, sir.
Right, so we are looking at some mathematical terms. Yesterday we have seen, yeah, can someone please tell me what we have seen yesterday? Very basic modular operations that we have seen yesterday, and the modular arithmetic that we have seen, and how to find the modular arithmetic for the larger numbers that we have seen yesterday. So today we'll try to continue some more mathematical terms which you already know, but we will see some advancements in those. The first one is co-prime numbers. Now, does anyone know about this or relative prime numbers? Okay, so this is it seems this is the new term for you. So I'll give you the term that you know, GCD of, let's say, A and B. Okay, you know that greatest common divisor for two numbers. If it is 1, okay, then both the numbers A and B are called as co-prime numbers, or they are relative prime numbers to each other. Okay, so this is the condition for being this statement true. Okay, so this is a very important concept that is necessary for cryptography. Okay, so how this concept is used in cryptography or in mathematical algorithms, I'll give you that idea, but just remember this statement. Now, when we are talking about GCD, let's say now, yesterday we have talked about this term that if you know the greatest prime number, or if you can find out the one prime number which is already existing, the largest prime number, then you know all the world will look for you and will be behind for you to get that prime number. Now, why is that so important? Because the prime number factorization, if you think of the factorization, so when you do the GCD or when you do the modular operations, the factorizing any number is the important thing in the cryptography, and the prime numbers are very difficult to factor. Okay, so when you do the operations on prime number, it becomes difficult. So, and it is like when you are finding out the GCD of, let's say, two different prime numbers, okay, then you know even that will be a bit difficult. So what we will do is we'll study one algorithm that is called as Euclidean algorithm, or Euclid algorithm. Okay, now what is it? Just I'll give you the definition first, okay, and how it is used to used in cryptography. That I'll give you the examples. So it tells you that let me give you the example first. GCD of 27 and 21. And can anyone tell me what is the value? Very simple thing.
3.
Okay. Now let's say you're taking at least 10 or 20 seconds for this calculation. Okay, for the small numbers. But think about the numbers which are 300 or 600 digits long. Okay, I'm talking about the number of digits. Okay, so right now we are dealing with 2-digit number. Think about 300 or 600 digit number. Okay, so how to find out the value of GCD value of such large numbers? Okay, so you can't do the operation like you have learned up till now, right? So the factorization is not that simple. Now what is the procedure? So this Euclidean algorithm will help you to achieve that, or to get the answer, okay, for the larger number. Now for that, let me give you the idea. First of all, what you do is, let's say this is a 27, okay, and this is a more or less 21, okay. So when you deduct 21 from 27, what is remaining? 6. Okay, so next time what you do is, this 21 you have to divide into these sections, whatever is the remainder. This is the remainder, right? So yesterday we have seen one equation which gives you dividend equal to quotient into divisor plus remainder. Okay, so please remember this formula, because this is the very important formula in all the unit, as I've told you yesterday. So now the next step for finding out the common divisor, whatever is the remainder, what you do is you divide that 21 into equal parts of this. So how many equal parts of this can be divided? 6, 6, 6 will make 18, and the remainder is 3. Is it correct? So this 21 can be divided into 3 parts of 6, the earlier remainder, and the new remainder is 3. Okay, so now the new remainder will be making this part, 6 part, as this one, and then lastly you get 0 value, right? And this is how you can find out the GCD. Okay, so let me give you this is just a pictorial view. I'll give you the exact formula for that. So what I have done here is GCD of 27 and 21. Okay, so instead of doing this, what I'll do is equal to GCD of 21, okay, and 27 mod 21. So I have done this 27 mod 21. Can you tell me what is the value of 27 mod 21?
6.
Yeah, it is 6. So 21 and 6. So instead of doing 27, 21, I have reduced the problem to GCD of 21 and 6. Okay, I'll still further reduce this as GCD of 6 and 21 mod 6. Can you give me the answer for 21 mod 6?
3.
3.
3. So it is GCD of 6 and 3. Okay. So I'm just giving these steps here, right? And GCD of 6 and 3 is 3, as simple as that. So to find out the GCD of 27 and 21, okay, these are the steps that you have to follow. Okay, and this is the Euclidean algorithm. Okay, so I'll give you the definition here. If you want to find out the GCD of A and B, considering that A and B are two large numbers of 300 and 600 digits, so it is equivalent to GCD of B and A mod B. Okay, so, and this process you have to do recursively. So once you have got the answer, you still have to continue, right? And you have to repeat this process until you can't, do the operation. So here you can't actually do further reduction, right? So you can stop here. Okay, so this is the Euclidean algorithm that is needed for the cryptography. Okay, I don't know, there's some light behind this. Okay, so have you understood the concept? We'll try to solve few more problems here. I'll give you the problem as okay, all of you will try this now. GCD of 161 and 112 with the Euclid algorithm. Okay, or what you can do is you can try this. So I can give the first step as GCD of 112. So B I'm taking as a first argument, and second one is 161 mod 112.
So 161 mod 112 is 49.
49. Okay. So this becomes GCD of 112 49. Is everyone getting the same answer?
Yes, sir.
Right. So the next step is you again work on this one. Okay. So let me just take to this side. GCD of, you can reduce it further. 49 will be changing its position, and 112 mod 49.
So it is 14.
So GCD is
49, 14.
1 4.
Yes, sir.
Okay. So next step is GCD of 14, 49 mod 14. What will be that?
GCD of 14, 7.
7. And that will be
7.
7.
right. So this is your answer. And this is how you solve the problem. Now this is one method. Okay. As I have told you, this equation, dividend equal to quotient into divisor plus, I'm sorry, am I doing it wrong? Is that the divisor or dividend?
Dividend.
And this will be the divisor.
Yes, sir.
Okay. So let us try to solve this problem with this equation. Okay. It's a very simple thing. 27 equal to 21 plus remainder and quotient. What is the quotient here? As a first step,
1.
1 into 21 plus 6. Right. Next time, what you do is you take the divisor on the left hand side. Okay, so you do this. You find out the new quotient and new remainder. What is that? So this actually
3 and 3.
Yeah. So this 3 and 3. Right. So for the next one, again, what you can do is 6 you'll take on the left hand side. What is the quotient here? 2
and 0.
and 0. As soon as you get the 0 as a remainder, not reminder, I'm sorry, the previous remainder is the answer. Okay, so you have to keep this in your mind. Again, if you want to solve this one, okay, we can do this as, where should I? Okay, I'll do this. 161 equal to 112 plus remainder. What is the quotient here?
1.
1. And what is the remainder? It will be
49.
49. Okay, because we have already calculated that. Next step, you take the divisor here and remainder here. Next step. So 112 equal to 49. What will be the quotient?
So 2 and 14.
2 and 14. So we have already got these answers. So you just have to arrange these. 49 you are going to take on the left. And this is the new. So 14 into
3 plus 7.
3 plus 7. And next time 14 will be taken on the left, equal to 7 into 2 plus 0. As soon as you get the 0, previous remainder is the answer. You got these two methods. So basically, it looks very simple for these numbers, but it becomes difficult for the larger numbers. I'll give you one more example. Find out the GCD of 973 and 301. GCD of
30170.
okay,
301.
30170. Okay.
Seven to 21.
70, 21.
Yes.
Okay, good. Then GCD of
21-7.
21.7. Good. And this is the answer.
3.
Okay. Let us write the same thing in in different variant, like 973 equal to 301 into plus 70. I hope this is 3. 301 equal to 70 plus. Am I writing it correct? What is the quotient? So what are these quotients?
So 4 and 3.
4 and 3. Okay. I hope everyone has got this concept.
In the previous one, shouldn't the GCD be 7?
Okay, the answer here,
Like- Yes, sir.
it's not 3, it has to be 7. Correct. So good. Should have these. So if you have understood this, we can go ahead. Or if you have any doubts, we can, discuss. So what we have done is we have just seen 3 concepts. One is the co-prime. Whenever there is a GCD of 2 numbers are 1. Then the second concept is Euclidean algorithm, which gives you this. This is the recursive. Actually, you can write a program for the large numbers to find out the GCD, right? This way, it will be the recursive program. And these are the couple of methods. Now, the new concept is Euler's phi function, or it is called as phi of n. Okay. Now, what exactly is this one? Now, it tells you, I'll tell you the definition first. If you have a set of numbers 0, 1, 2, 3 till n minus 1. How many numbers are these? N numbers. Okay, so if you have these numbers, then GCD of, you have to calculate this set, GCD of 0 with n, then GCD of 1 with n, GCD of 2 with n, and so on, till GCD of n minus 1 with n. Okay, you have to keep calculating all the values here. Okay, and you have to count those values which are 1. Okay, that means you have to find which are the sets of two numbers they are which are co-prime to each other. Okay, so I want to find the number of relative prime numbers in this set. You got this concept? And phi of n gives you that number co-prime numbers. Okay, so let me give you the example directly. Let us try to find out. Let us take the value of n as 6. Okay. So what will happen is you have to find out GCD of 0 and 6, GCD of 1 and 6, GCD of 2 and 6, five and 6. Okay, because Z will have 0 to n minus 1 values. Okay, I have not written the set here, 0, 1, 2, 3, 4, and 5. So this will be Z set. Okay, and you have to find out these values. Can someone tell me these values? I'll give you a minute. What is GCD of 0 and 6? 6. That's correct. This one?
1.
Okay. This one?
2. 3. 2. 1.
Okay. Now, once this you have these values, you have to count these numbers which are ones. Okay, so what I have got from this is a phi of n is 2 when n is equal to 6, or you can say phi of 6 is 2. Okay, so we'll now quickly calculate the two sets. One is n equal to 5 and other one is n equal to 7. Zero, 5. I hope you're calculating. Zero, 5. 1, 5.
So for 1 5 it is 1.
Hmm?
It is
2, 5.
also 1.
Okay.
3 5 would also be 1.
Hmm?
And 4 5 will also be 1.
Okay. This one?
7 1 1 1 1. So for everything it would be 1 only.
Okay. So can you give me some inference or conclusion here?
For a prime number, we are getting n minus 1.
Great. So for prime numbers, phi function gives you n minus 1. Here also we are getting 6. So phi of 7 is equal to 7 minus 1. Okay. So this is a very important concept again, that the co-prime numbers, when you consider the prime numbers, the co-prime numbers are n minus 1. Okay. And whenever you are dealing with the next level of cryptography, that is public key cryptography, this is a very important concept. Okay. There is one more thing which is for the non-co-prime numbers. I'll give you the formula. It's a very different formula, but what I can suggest is we will not go for that right now because it is not needed right now. So this is a base, base for the public key cryptography. So tomorrow we are going to study, not tomorrow, that in the next lecture, we are going to study the public key cryptography. And it's a very great concept if you are working in, the public key cryptography is used everywhere. Most of the places, the digital signatures, the application of digital signatures, all the websites, everywhere, most of the places, this public key cryptography is used. Even with the ATM cards, what happens is when you put the ATM card, there is a private key which is burnt on your card, and there is a public key of that particular bank. Okay, so and then the encrypted communication happens whenever you put the card into the ATM machine. So these are some of the applications of public key cryptography, and this is whatever we have seen up till now: co-prime numbers, Euclidean algorithm, and fee function are the base for the public key cryptography. Okay, so I'll try to implement whatever we have seen here. We'll try to implement in the next lecture. So if you have any doubts, please let me know.
मेरे को सुबह करनी है अभी बारिश रुक गई बारिश क्या करना है आपको